Alright, video 3. We got 5 more examples to do. Let's see how quickly we can get these done. Alright, so this time it says use implicit differentiation to find the partial of z with respect to x and then the partial of z with respect to y. And the reason we need to use implicit is because z is being multiplied by the x and the y over here. So it's very much like implicit derivatives in ABBC, where you couldn't explicitly solve easily for z. I can't solve this thing easily for z and put everything into terms of just x and y. So we're going to have to use the same principles that we did before. So dz dx, partial of z with respect to x. Alright, so we're going to take the derivative of x, the independent variable, just like it was a regular derivative. So that's 2x. Technically, since it's implicit, it would be 2x times dx dx, but dx dx is 1, so we don't write that. Plus the derivative of y squared, but that's 0. It's a constant. Plus the derivative of z squared. Now this is where the implicit comes in, plus 2z, and then it's a chain rule, so the derivative of the z part is dz dx. And then we do the derivative of the right side. Now you have to be a little bit careful on this. Remember that x is your independent variable and z is your dependent variable. So you can in some way see this as a product rule. Well, it is a product rule, but what you can do is you can maybe attach the 3 to the x, and don't forget y is constant now, so you can attach y to the z, or technically you could put the whole 3xy as 1 or the 3yz as 1, keep the other one. It doesn't really matter. You should end up getting the same thing, but you got to connect your constants to one of the two variables here. So this is going to be, let's see, a product rule. The derivative of the first is 3 times the second, yz, plus the derivative of the second is going to be y times dz dx times the first, which is 3x. So it looks like if we're going to try and solve this thing for dz dx, we need to isolate these on the same side of the equal sign. So I am going to go ahead and move this term to the right side. I'm going to subtract the 3yz from both sides. So we should get 2x minus 3yz equals 3xy, just rewriting this, dz dx minus 2z dz dx. And now that we've got all the dz dx's on the same side of the equal sign, we can factor that out. So 2x minus 3yz equals 3xy minus 2z, dz dx. And then to solve for dz dx, we're going to divide both sides by what's in the parentheses here. So we're going to get 2x minus 3yz over 3xy minus 2z, and that equals the partial of z with respect to x. Alright, and then it says to find dz dy. Let's move this down a little bit. dz dy. Well, if you're really thinking about it, it's going to be very, very similar. This time x is constant, so anytime we have the x here, that's going to be 0. This is going to be your independent variable, so on the left-hand side, it would be 2y instead of 2x, and the z part is still going to be 2z, except it'll be dz dy this time, because this is what we're going to try and solve for, is dz dy. And over here, it's exactly the same thing. Really, all that's going to happen, if you're really thinking about it, and I'm not going to walk through all these steps, is that wherever I had x up here, it's going to become, wherever I had a y up here, it's going to change to an x. So really what we should have when you finish it, and you can go ahead and check this, um, is going to be 2y minus 3xz over 2z minus 3xy. And that would be dz dy. Again, you can go ahead and go through the process there and check it, but that's what you should end up getting. And if you have these exactly backwards, if you had 3xy minus 3xz minus 2y and 3xy minus 2z, it just means that you took your your partials and moved it to the other side of the equal sign. That's all, and that's fine. It's the same thing. All right, number 10 says find all second derivatives of u equals e to the negative s sine t. Second derivatives, just like you would do before, is going to be the derivative of the derivative. However, it's going to change things a little bit. We're actually going to have to find, well, here, I'll just walk through it with you. First, let's find the derivative, the partial with respect to x. So the derivative of u partial with respect to s. So here's the only s, that means sine t is constant. So the derivative of e to the negative s is negative e to the negative s, and don't forget to multiply it by sine t because it's just a constant, it stays there. Then let's find the partial with respect to t. Okay, and again, all of this is now constant, and this is the only thing that has a t in it, so this is going to be e to the negative s, and the derivative of sine is cosine t. Now when it says find all second derivatives, now I have to take the derivative of the derivative, but that means I've got to take the derivative of the partial of s with respect to s again. And that would be the partial of s twice. So it would be the second derivative of s with respect to s and then s. So in this case, we're going to take the derivative of this with respect to s. Well, again, this is the only part that changes, so this is going to make that negative become positive, so it'll be e to the negative s sine t. Again, sine t is constant here. Same thing over here. The derivative of t and then t. So again, this is the only thing that changes. Well, the derivative of cosine is negative sine, so we'll throw the negative out in front. And there's our second derivative with respect to t. Now, this is the big change here. I also have to do the partial with respect to s, but then I could also take the partial after this of t. So now that I've gotten the partial with respect to s, now I'm going to do the second derivative, but now it's going to be with respect to t. So now this is going to change. So the derivative of sine t is cosine t times this. So it'll be negative e to the negative s cosine t. Same thing over here. I could also go with the first partial with respect to t and second partial with respect to s. So now s is going to be the thing that changes here, and cosine t will be held constant. So this will become negative e to the negative s. Cosine is constant, so cosine t. So you really have four partials when you have two variables. And if you had three variables, you're going to have six partials when it comes to second derivatives. One thing I need you guys to notice, if you look carefully, the partial with respect to s and then t, and the partial with respect to t and then s is exactly the same thing. These are equivalent to each other. And this is actually a theorem which is called Clairaut's theorem. And what that theorem says is the partial second derivatives are commutative. So it really doesn't make any difference which way we go. If we go with respect to s, then t, or with respect to t and then s, you should get exactly the same thing, and you always will, actually. This theorem is much more long to prove, so we're not going to go through the proof. But for this example, at least you can see it, and this will always hold true. This theorem has been proved. We are just not going to do that in this case. All right, moving on. Verify the conclusion of Clairaut's theorem holds true for this one. So we're just going to verify it for this one in particular instance right here. So we want to do the partial of u with respect to x and the partial of u with respect to y, and then we'll do the second partial with respect to the other variable and see that they're the same thing. All right, with respect to x, so this is going to be a product rule. I've got x here, and then I've got an x inside the sign. So product rule, derivative of the first times the second plus derivative of the second, so it's going to be a bit of a chain here, is cosine x plus 2y times the derivative of the inside, but that's with respect to x, so that's 1, that's constant, that's 0, so I don't have to write the times 1, and then times the first, which is x. So let's clean that up a little bit. That is sine x plus y plus x cosine x plus 2y. This over here should be a 2y. Let's fix that. 2y there. Okay, so let's do the partial with respect to y. Well, the only y is in here, so this is held constant. So really we're going to get x sine, oops, not sine, cosine. So x cosine x plus 2y times the derivative of the inside. Derivative of x is 0, derivative of 2y is 2. So that's the partial with respect to y. Now let's take the second partials, but we only need to do it with respect to the other variable. So uxy, so the sine of x plus 2y, derivative is going to be cosine x plus 2y times the derivative of the y part this time for the second derivative, that's 2. So that's going to come out in front. Now the derivative of this one with respect to y, once again, x is held constant. So it's just going to be the derivative of cosine, which is negative sine. So let's make this a minus sign. Negative sine x plus 2y times the derivative of the y part, which is 2. So let's double check now. We should get exactly the same thing. So we've got the derivative of y x. So now we're going to take the derivative of this with respect to x. This is a product rule. Product of these two, because I've got x in both. So the derivative of the first times the second. And so far that's a good match. Plus the derivative of the second. The derivative of the second is cosine, so I mean it's negative sine, so we will have a minus sine of x plus 2y times the derivative of y, which is 2, times the first. What did I mess up here? Because this is going to give us a 4x. I must have messed something up over here. Multiplied by 2. Oh, no, I messed it up over here. You guys probably caught it before I did. There is no extra 2 out here because the derivative of this time is with respect to x, which is 1. So I'm going to go ahead and throw the 2x out in front. So this is right. And as you can see, these two things are equivalent. So Clairaut's theorem, at least for this in particular case, did work. And again, it will work for all of them. it is has been proven. All right. If the function of x, y, z is this cosine function here, we want to find f of x, y, z, and I'm sorry, the partials of x, y, z, and then the partial of y, z, z. Okay, that's an interesting one. Let's do the first one. We want to do the partial of x, oops, first, and then we'll do that with respect to y, and then that with respect to z. So the partial with respect to x, well, it's this cosine, so it'll be negative sine of 4x plus 3y plus 2z times the derivative of the inside with respect to x is just going to be a 4. So let's just put that out front. It's be negative 4 sine. There's the partial with respect to x. The partial with respect to y, I'm sorry, x then y, moving in order, means I'm now going to take the derivative of this with respect to y. So it's going to be, let's see, the derivative of sine is going to be cosine, so it's negative 4. I'm going to hold off writing that now. Oops, not sine, cosine. Of 4x plus 3y plus 2z, but I'm also going to multiply it by the derivative of the y portion, which is 3, so we should have a negative 12 out front. And then finishing this one off, x, y, z. So now I'm going to take the derivative of this whole thing with respect to z. Again, I'll have a constant out front. The derivative of cosine is negative sine, so it's going to change that to a positive. So we'll have positive sine 4x plus 3y plus 2z times the derivative of the inside, which is 2 with respect to z, so that's going to make this 24. So there's your partial of f of x, y, z in that order. And then it wants us to do f of y, z, z. Interesting one. F of y first. So the derivative of this with respect to y, negative sine, but then times 3 because of the y. So 3 sine 4x plus 3y plus 2z. And then the derivative with respect to z, I'm sorry, I keep forgetting to put the first one in there, yz, is going to be the derivative of this thing with respect to z will get multiplied by a 2. Derivative of sine is going to keep the same sign, so it's going to be negative 6 cosine 4x plus 3y plus 2z. And then the last one, f of y, z, z, just means I'm doing z again. So with respect to z again is going to be multiplied by another 2, and it's going to become a positive sign. So it should be positive 12 sine 4x plus 3y plus 2z. And what you should notice is these are not commutative because we did not follow the same order. So none of this stuff should actually equal itself. All right, this is our last problem. I do want to cover one thing when we get to this. You guys saw the notation in 2 dimensions, and I kind of want to go back to this. A lot of people always had questions what this meant, why it was written like that. This will actually start to answer some of that, so I'll come back to this at the very end. So what we want to do is we want to find the indicated partials, where w is given as x over y plus 2z. We want to find these two partial derivatives. This says I want to find the third partial derivative of w with respect to z, y, and x. And actually the way you read it is backwards. This is the first partial that you do. I'm not sure why it's written this particular way backwards, but this is always the way it's done. This is the first partial, and that is the last partial. So that's the first, then dy is the second, then dz is the third one in this case, or the last one. It works right to left on the bottom. I'm not really sure why that is. So let's go ahead and find this one, and then when we get to the second one, it'll help me explain this. So we want to find first the partial of w with respect to x. So again, remember the x is the only thing that's changing. The rest of this stuff is constant. So it's really like x times 1 over that. So really the first partial with respect to x is just 1 over y plus 2z. And then we work our way backwards. So now we want the partial of w with respect to x and then y. So now we're going to take the derivative of this thing with respect to y. But remember, you could rewrite this as y plus 2z to the negative 1 power. So we'll bring the negative out front, reduce the power by 1, and then the derivative of the inside of here with respect to y is just 1. So this is going to give us negative 1 over y plus 2z squared. And then the last thing we need to do is the partial. Oops, that should be a second partial. Now it's the third partial with respect to x first, then y, then z. So now I'm going to take the partial of this with respect to z. I'm going to take it from this form. It's just going to be easier. So we'll bring the negative 2 out front, so we get 2y plus 2z times the derivative of the inside of here, but that's just going to be 2 times the z part. Oops, that's a negative 3 power. So we should end up with 4 over y plus 2z cubed. All right, and that is the third partial of w with respect to x first, then y, then z. So really what this is, this piece right here, is exactly the same thing as saying we want to find w of x, y, z in that order. That's what that means. All right, so now let's take a look at this one. And I'm going to do this one in a different color just to change things up here. Again, this one will kind of relate to what we were doing in ABBC. It wants us to find the third partial of w. It says to find it with respect to y first, then with respect to x, and then with respect to x again. That's what that little squared right there means. So let's go ahead and do it, and then I'll explain it as we go. So dw dy is going to be, so if we take the derivative of this thing with respect to y first, again, we can bring that whole thing up and make this x times y plus 2z to the negative 1. And then we'll bring the negative out front, multiply it by the constant x. So negative x, y plus 2z now to the negative 2 times the derivative of y, which is 1. So here we get negative x over y plus 2z. And then we want to do the partial with respect to y, and then 1 of the dx. And let's go from this form. If we bring the negative 2 out front, because we're now doing this with respect to x, so we're going to bring the negative 2 out to the front. And, I'm sorry, this is negative x times all of this. So really the negative x is going to become a negative 1. So what we get is negative 1 y plus 2z to the negative 2, because all of this is constant. So really the derivative of negative x is just negative 1, which really could be written as negative 1 over y plus 2z squared. And if you're really thinking about it, this makes sense. This is the same as this, because this is Clairaut's theorem, saying that I took the partial of w with respect to y then x. Here I took it with respect to x then y. And again, I forgot my little squared notation because it's the second derivative. So these two things actually make sense if they're equal. But then the third one says I want to take the third derivative of w with respect to y, with respect to x, and then with respect to x again. But that's the same thing as the third derivative of w with respect to y and with respect to x squared, or x twice, basically. So we're going to take the derivative of this right here with respect to x again. Well, look at this. No x. If there's no x, there's no independent variable, so this whole thing is a constant, which means that the third derivative here is 0. That's really kind of nice. that it works out that way. So let's circle this whole thing back real quick. This one's going to be just over 25 minutes, so I do apologize. Um, but this really means when you're taking the second derivative, this is why it's written like that. This is, whoops, that's purple. Well, how did that happen? Okay, we're not having purple right there. Sorry. I meant to hit black. Um, so what this is really saying is I was taking the derivative with respect to x and then the derivative with respect to x again, which is why a second derivative is written in this form. It's the oops, two dimensions. It is written as the derivative, the second derivative of y, or the derivative with respect to y twice, of dx over dx, which is the same thing as the second derivative with respect to y of dx squared. That's why that notation is written like that, and this is what you're going to see here with partial derivatives, that this is the way it's written. So it just means you're going to take the derivative of this thing twice, the x backwards twice. Alright, that is way longer than I intended to make all of these videos, but hopefully that gives you enough. There is a web assign attached to this, and I'll explain in the Google Classroom notes how all that's going to work. Alright,